So 2 class periods ago, we talked about the parallel postulate, and that allowed us to prove that the 3 angles of any triangle add up to 180. And then last time we proved that if a triangle has 2 equal sides, it has to have 2 equal angles and vice versa. And a triangle with 2 equal sides is called isosceles. So this fact is called the isosceles triangle theorem, the isosceles triangle fact. The equal sides and the equal angles are opposite each other, sort of across the triangle from each other. And then we started looking at polygons. And we talked about what makes a polygon a polygon. We talked about the different prefixes to know up to the number 12. If you really want to, you can ask Google what the Greek name for a 48-sided polygon is. And then we drew different polygons with a different number of sides, drew diagonals from one vertex, and we noticed this pattern, which then led us to a formula that the angles of a polygon add up to 180 degrees times the number that is 2 fewer than the number of sides. That's the number of triangles formed when you draw all of the diagonals from one vertex. And then an exterior angle makes a linear pair with an interior angle. And so at each vertex, there's 2 angles, an interior angle and an exterior angle, and they add up to 180 degrees. And however many sides the polygon has, that's how many sets of linear pairs you're going to have. And if you take the n linear pairs and subtract the measures of the interior angles, you're left with the exterior angles always ending up being 2 groups of 180 or 360 degrees. Always. Because if you subtract n minus 2 groups of 180 from n groups of 180, you're going to have 2 groups left over. So that led us to, this is just the summary of those 2 facts. If you add up the interior angles, you always get the quantity n minus 2 times 180 degrees. If you add up the exterior angles, you always get 360 degrees.
What's the degree of the exterior angle of the polygon had 40 sides?
Okay.
And I could not get it.
Okay.
So I would take 360, divide that by 40,
Mhm.
that would be my exterior angle.
Right. If it's equal angular.
Yeah.
Yeah.
It's a set of 8.
Right. 40 gone. Right. Yeah. So if we have a 56-sided polygon and we want all of the interior angles added together, we end up taking 54 times 180. If we want all of the exterior angles added together, that doesn't depend on how many sides we have. It's always 360. And then this is what you were talking about. If I know that my polygon is equiangular, which regular polygons are equiangular, then I just have to take those 2 previous numbers and divide by the number of sides, which is equal to the number of angles, and I'll get how big each one is. And we know at each vertex there's a linear pair, so we can use that to check our answer. Or if we've already figured out one of these, we could use this equation to figure out the other one. And then this last equation, E equals 360 degrees divided by N. If we rearrange that equation so that N is by itself, then we get 360 divided by E. So this is a problem like you were talking about, except this time 8 sides instead of, in your case, 40. So if I want to know what all of the interior angles add up to, I end up taking 6 times 180. So if I want to know how big each of them is, then I'm going to divide that by the fact that this number is split into 8 equal pieces because there's 8 angles. So each of these angles then would be 135 degrees.
When they talk about that extra angle, they're not talking about from one side all the way to the other, just one half of that.
They're talking about one of these pink angles.
That's what we're gonna do. Look at the
Right,
whatever you're into.
right, right. Or you can just take 360 and then divide by how many. So you can do it either way. So in this case, if I take 360 and divide by 8, since I had an octagon, then each of these is 45 degrees. And then, so what we're saying now is that each of the interior angles is 135 degrees and each of the exterior angles is 45 degrees. And if we add those two numbers, we get 180 like we're supposed to. And then we can go backwards. If we know how big each exterior angle is, then we can just take 360 and divide by each exterior angle, and that'll tell us how many sides we have. If they give us the interior angle, this is probably the hardest type of all of the problems because it kind of involves 2 steps. If they give us each interior angle, the easiest way to find out how many sides it has is to first find out how big each exterior angle is. And once you know how big each exterior angle is, then you can find the number of sides. And what I was just doing in this last hour was I created a online tool that will draw a regular polygon of however many sides I want. So here's a picture of a 36 gon, a regular 36 gon. And to us humans, it's hard to tell the difference between, I mean, that looks like a circle, right? But technically it's not. It's a polygon, but each of the exterior angles was only 15 degrees. That was that problem. That was the other one. I put this in the wrong page. I wanted it here. There we go. So when each interior angle is 170 degrees, that's almost a straight angle. And then each exterior angle is only 10 degrees. So even if I were to take this line segment and extend it, what we're saying is that this angle is 170 degrees and this angle is 10 degrees. But now that I've made this, and I've made it so you can choose any number of sides up to 100. So in the previous picture, it was a 24-gon. And in this problem, each exterior angle we were given measures 15 degrees. And each interior angle, if we wanted to figure that out, that would have to be 165 degrees so that they add up to 180. So if E equals 15 degrees, then 1 n equals 360 divided by 15. So we get 24. And since the interior angle plus the exterior angle make a linear pair, they have to be supplementary. So if the exterior angle is 15 degrees, if we subtract that from both sides, that gives us 165 degrees. And if we wanted to know what all of the interior angles add up to. We would take the 24 and subtract 2, multiply that times 180. So whatever we get. So 3,960 degrees. Notice that that should be the same then as taking 24 groups of 165. And that should be the 3,960 as well. So if we did all of our arithmetic correctly. So we get the same number. So that's good. Where did that, I thought I pasted that picture in here. Where did I put it? Oh, right there. Okay. Good. So when the number of sides gets bigger and bigger and bigger, the polygon starts looking more and more like a circle. And we can go through this whole process for any number of sides. It's kind of neat to look what happens for some of the shapes with a smaller number of sides. So we know that the sum of the interior angles is 180 degrees. We don't really have to use the formula. We just know the triangle sum.
When you get into like 6 million sides,
Mm-hmm.
that number, your angle is like point something.
Right. Right.
per one.
Yep, exactly. In decimal form, it'd be 0.0000 and a whole bunch of. Exactly. And in fact, well,
For infinity, yeah, any side.
well, that's. You can't actually get to infinity, but you can think about getting closer and closer to infinity. And as you do, each time we go up a number of sides, if there's 4 sides, quadrilateral sum is 360, divide that by 4, you get 90. And the exteriors are also 90, and 90 plus 90 is 180. As soon as you have more than 4 sides, the interior angles are always obtuse and the exterior angles are always acute. When you have 4 sides, they're both right angles. But the more sides that you have, the bigger and bigger the interior angles get and the smaller and smaller the exterior angles get. So in the limit, if there were such a thing as an infinitely many-sided polygon, then each interior angle would be 180 degrees and each exterior angle would be 0 degrees. But those aren't really angles. What? Yeah, yeah. Yeah, yeah, to something that's almost a circle, we call it, sometimes we say degenerates, but the polygon all of a sudden magically just turns into a straight line. Mm-hmm. But what that tells us is this is something we don't quite get to in this class. If we do look at a circle, and we pick a point on it, we could draw the line in that same flat surface. And I'm going to use my machine to cheat. There is one, at any particular point on a circle, there is one line in the plane that is what we call tangent to the circle. So it just touches the circle in exactly one point. And that line could be thought of as that infinite polygon that all of a sudden becomes a straight line. And so this angle is a straight angle, right? It's going to be 180 degrees. I should have probably drawn the center of my circle. It's around here maybe. But notice that if I draw from the center to that point, that angle is going to be a right angle. It's going to split that 180 degree angle exactly in half. And when we go to find a formula for the area of a circle, we use that idea. So let me show you one more thing. Let's take the number of sides down to something more reasonable. Whenever you have a regular polygon, in this case, I think there was 10 sides. If I count the very top as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have a regular pentagon, and we have a circle. That circle has a center that's about there. And I could draw in the radius, a line segment from the center of the circle and the decagon. And the thing that makes a circle is that every red point that you see, not just the ones that are highlighted, but the curve that makes the circle, they are all the same distance from the center. So all of these smaller triangles are isosceles. And if that distance is x, we would say the radius is x. And this distance, I'm going to call that A. That's called the apothem of the polygon, the decagon, the regular decagon. And that's going to be the same for each of those 10 green triangles. And the idea is that the area of the regular pentagon is almost the area of the circle. It turns out that if each side of the regular decagon has length S, it turns out that the area of any triangle can be thought of as half the area of a rectangle. So 10 times the area of one triangle is almost the area of the circle. The area of the triangle is 1/2 that number S times that number A. And as the number of sides gets bigger and bigger, the polygon gets closer and closer to the area of the circle. And also the perimeter of the polygon is almost the perimeter of the circle. And we can use those ideas to help us figure out why the formulas that we end up with for circles is what it is. The perimeter of the regular 10-gon is just 10 times the number S, whatever it is. But this is just a regular 10-gon. If we look back at when we had our 36-gon, it already looks like it is a circle, even though it's not. And each of those isosceles triangles are really skinny. And the apothem is almost as big as the radius. So the bigger and bigger the number of sides get, the closer and closer these 2 points get, the skinnier and skinnier the isosceles triangle gets, and the number A gets closer and closer to the number X. And that's one way to find the formula for the area of a circle, is to what happens if we let that go to infinity. But we don't quite have all the tools we need for that.